Hey there, and welcome. Have you ever looked up at the sun and just wondered, how do we actually turn all that light into the electricity that powers our world? Well, in this explainer, we're going to break that whole process down, from a single particle of light, a photon, all the way to the power grid. Let's dive right in. So here's our game plan. We'll kick things off with the sheer scale of the sun's energy. Then we'll get into the really cool stuff, the two main ways we capture it. First, by turning light directly into electricity, and second, by harnessing its heat. After that, we'll see how it all gets to our homes, and we'll wrap up with a little peek into what's next for solar. Okay, first things first. Before we can even talk about converting solar energy, we really need to get our heads around just how much of it there is. It's a lot. Think about it. The sun isn't just a source of energy. It's pretty much the source for everything. It's this constant, massive river of power that drives our weather, our oceans, and, all life on Earth. Everything else is really just a ripple effect from this incredible star. And if you want to put a number on it, scientists use something called the solar constant. Just imagine a 1 meter square, about the size of a small card table, floating way up at the edge of our atmosphere. Every single second, that little square gets blasted with 1,367 watts of solar power. That's enough energy to light up more than a dozen of those old, super bright incandescent light bulbs. Every second. Constantly. So how in the world do we capture all that energy? Well, the first big technique we're going to look at turns light directly into electricity. It uses this amazing process that almost feels like magic, called the photovoltaic effect. The absolute key ingredient for this to work is a special kind of material called a semiconductor. You've probably heard of the most common one, silicon. It's interesting because it's not a great conductor like copper, but it's not an insulator like rubber either. It lives in this perfect little sweet spot right in between, and that's what makes it the ideal building block for a solar cell. Okay, so pure silicon by itself won't do much for us. We have to tweak it a little bit using a process called doping. What we do is create two different types. On the left, we've got p-type or positive silicon. We add specific atoms that create these little holes, basically spots where an electron is missing. On the right, we create n-type or negative silicon by adding atoms that give us extra free electrons. This intentional positive and negative imbalance is the whole secret to making a solar cell work. All right, so when you put these two special layers of silicon together, it's like a tiny four-step dance that happens automatically to turn light into electricity. First, you create the junction, which forms a barrier, then sunlight comes in and provides the energy, and finally, that energy pushes electrons, creating a current. Let's break down exactly how each one of these steps works. So, the second those two layers touch, something really cool happens. Those extra electrons from the n-type side immediately jump over to fill the holes on the p-type side. This flurry of activity creates a thin but permanent electric field right there at the junction. The best way to think of it is like a one-way street, or maybe a gentle slope that electrons can now only easily travel across in one direction. And now for the magic moment. A photon, a single particle of light from the sun, comes flying in and bam! It strikes the silicon. If that photon has enough energy, it transfers it to an electron and knocks it loose from its atom. This is it. This is the exact instant that solar energy gets converted into electrical potential. And here's the payoff. That electric field we created at the junction, now it does its job. It acts like that slope we talked about, pushing the newly freed electron over to the n side. If we connect a wire between the two sides, we give that electron a path to travel. And that flow of electrons through a circuit, well, that is electricity. Now you have to remember, this whole amazing process is happening at a totally microscopic level in just one solar cell, and it only generates a tiny bit of electricity. So to get any real, usable power, we have to scale it way up. We wire individual cells together to form modules, we assemble those modules into panels, and then we combine those panels into massive arrays. It's that teamwork that creates the power we can actually use. All right, so that's the photovoltaic effect. But turning light into electricity isn't the only trick up the sun's sleeve. The second major technique is actually much more direct. We just harness the sun's thermal energy. Yep, it's heat. And this really breaks down into two main approaches. On one hand, you've got passive solar. This is all about smart design, right? Like using a big sunny window to heat up a room without any moving parts. And on the other hand, you've got active solar, which uses things like pumps and controllers to physically move the sun's heat around. Check this out. It's a perfect example of passive design. You have a thick, dark wall that faces the sun, and it just soaks up heat all day long. A glass layer on the outside helps trap that heat. As the air in that gap gets warmer, it naturally rises and flows into the house through vents at the top, while cooler air from the room gets pulled in at the bottom. It's a completely natural heating loop. No pumps, no fans.
You can see the exact same idea at work when it comes to heating water. The passive system on the left is super simple. The sun heats the water in the collector, and because hot water rises, it just naturally flows up into the storage tank. The active system on the right adds one key component, a pump. That pump forces the water to circulate, which makes the whole system more efficient and gives you more control.
And if you think that's cool, check out what happens when you take solar thermal to an industrial scale. This is a concentrated solar power plant. You have a whole field of mirrors that all track the sun and focus its light onto one single point, on a central tower. This generates incredible temperatures. We're talking over 1,000 degrees Fahrenheit. That heat boils water, creates high-pressure steam, and spins a turbine to generate electricity, just like a traditional power plant, but with the sun as its fuel.
So, we've covered how to generate energy from the sun's light and its heat. Now, let's bring it home. How does that energy actually get to us and connect with the bigger power grid?
When you get a solar PV system, you basically have two main options. On-grid systems are connected directly to the utility. You use the power you generate, and if you happen to make extra, you can often sell it back to the grid. Off-grid systems, on the other hand, are completely independent. That gives you freedom, but it means you absolutely need a big battery bank to store energy for nighttime or cloudy days.
So, why go solar in the first place? Well, the advantages are pretty compelling. These systems are totally silent, they produce clean, non-polluting energy, and they are incredibly reliable and durable with very little maintenance. And maybe best of all, you can install them almost anywhere, from a remote cabin deep in the woods to a skyscraper rooftop, generating power right where you need it most.
All right, so we've covered the fundamentals of how this all works. Let's wrap this up by looking at the really exciting part, where this technology is taking us. The future is, well, it's pretty bright. This is just a fantastic application of the technology. In Oman, they're building a massive solar farm, but its main job isn't just to create electricity for the grid. It's being built specifically to power a desalination plant. They're literally using sunlight to create fresh drinking water from the sea. It shows how solar can be this key that unlocks solutions to other huge global challenges.
You know, when you boil it all down, it comes back to this one fundamental truth, and this quote says it perfectly. Solar radiation is the most important natural energy resource. It's not just another option, it's the primary engine that runs our entire planet. Learning how to tap into it directly is one of the most important things we can do. So we've gone from a single photon knocking an electron loose all the way to giant power plants making fresh water. It's been an incredible journey. So I'll leave you with this question. As this technology gets even better, even cheaper, and more advanced, what new problems are we going to solve with the simple, immense, and beautiful power of the sun?